Hello everyone. In this presentation, we will see the working of the JK flip-flop. We have already studied about the SR flip-flop and D flip-flop. So what is the need to study the next type of flip-flop, that is the JK flip-flop? There must be some disadvantage in the SR flip-flop and the D flip-flop. That is why we have to move on to the next type of flip-flop, that is the JK flip-flop. So first of all, we will see what is the advantage of JK flip-flop, and then we will see the working of the JK flip-flop. Now in D flip-flop, we already know that there is a single input, that is D, which we call as the data input. So only two combinations are possible in D flip-flop, whereas in SR flip-flop there are two inputs S and R, so 4 combinations are possible in SR flip-flop. And it is always good to have a 4 combination as compared to 2 combination, but there is a disadvantage in the SR flip-flop also, that is when the clock is high and when the input S is 1 and R is 1, then it is the not used state. We don't use this state because in this case the output of the flip-flop is contradictory. Now we will try to make a flip-flop in which we can utilize this 1-1 state. We can do so by using a flip-flop which is known as the JK flip-flop. So first we will try to make a JK flip-flop from the circuit diagram of the SR flip-flop. So let us see what changes we will have to do to get our JK flip-flop. We see that this is the circuit diagram of SR flip-flop, and these are the two outputs Q and Q bar. Now we will take this output Q and we will give as input to this NAND gate. Similarly, we will take this output Q complement and we will give this as input to this NAND gate. So we will get a circuit as shown in this figure. Here we have taken the output Q and we have given it to the NAND gate, and similarly we have taken this output Q complement and we have given it to the first NAND gate. Now the input S has been renamed as J and the input R has been renamed as K, and so this is the circuit diagram of the JK flip-flop. Now let us see the working of this JK flip-flop. So let us consider the first case, that is when the clock is low. When the clock is low, then this input will be 0, this input will be 0, and since this is a NAND gate, so a low input will give a high output here and here. So we will get 1 and 1, and we know that this is the NAND SR latch, which we already know, and we have studied this SR NAND latch in the previous lecture class. So we know that when the input to the NAND SR latch is 1 1, then the output is stored, that is the previous value is stored. So in this case we will get the memory state. So when the clock is low, then we will have the memory. So the first case is when the clock is low, for any values of the inputs J and K, the memory will be stored, that is the value of Qn plus 1 will be the Qn, that is the previous state will be stored. Now let us consider the next case, that is when the clock is high and the value of J is 1 and K is 0. J is 1 and K is 0, that means that S is 1 and K is 0. So it is similar to SR flip-flop, and we know that in case from the truth table of SR flip flop that when the value of S is 1 and R is 0, then the output Q is 1 and Q bar is 0. So in this case also we will get the output Q as 1 and Q complement as 0 when the clock is high. So we have written this here, that is when the clock is high and the value of J is 1 and K is 0, then we will get the output Q as 1 and Q complement as 0. Now let us consider the next case, that is when the clock is high and J is 0 and K is 1. Now from the truth table of the SR flip flop we find that when the value of S is 0 and R is 1, value of Q is 0 and Q complement is 1. So in this case also we will get the value of output Q as 0 and Q complement as 1. So we find that all these 4 combinations till here are similar to the truth table of the SR flip flop. But this last case is different and this is very important. So let us discuss this case. In this case we find that the clock is high and the value of J is 1 and K is also 1. So we will have to find the value of Q and Q complement in this case. So before actually writing down the values of the outputs Q and Q complement, we will have to do the analysis in this circuit. For that we assume that the value of Q is 0 and the value of Q complement is 1. So let us write this. We have written the value of Q is 0 and the value of Q complement is 1. Now since this Q is input to this circuit, so this input will be 0, and since this Q complement is input to this circuit, so the input will be 1. Now we find that this is 0, so we will get a 0 here, so the output will be 1. So this output will be 1, this output will be 0. Again we get J is equal to 0, again we will get, this is a SR NAND latch, and we know that in case from the truth table of SR NAND latch that whenever the input is 0 and 1, then we are getting the output as 1 and 0. So in this case we will get 1 and 0. So we find that the output has changed from 0 to 1. Now again if we analyze the circuit with this output, we find that the value of this input will be 1 and the value of this input will be equal to 0. Now again if we do the analysis in a similar way, we find that we will be getting a value 1 here and a value 0 here, and from the truth table of the SR NAND latch we find that the output will be 0 and 1. In a similar way, if we do the analysis with outputs Q as 0 and 1, again we will find that the output will come to be 1 and its complement will come out to be 0. So we find that when we are giving the clock 1 and the value of J and K as 1 and 1, then we find that there is one pattern which we can see, that is the output goes on varying from 0 to 1, 1 to 0, 0 to 1 and so on. Similarly, the value of the Q complement also varies from 1 to 0, from 0 to 1, from 1 to 0 and so on. That is, the output is racing, and this is a very important concept in the digital electronics because we will use it in counters. So, what will be the output in this case? So, we can see that if the value of the output Qn plus 1 was 0 earlier, then our output will change to 1, and if the value of Qn plus 1 was 1 earlier, then it is changing to 0. So, actually it is the complement of the previous state. So, whatever be the value for the Qn, in this case we will get the output as Qn complement. So, in this way we have converted the not used case to the complement of Qn. This is known as toggling. Now, there is a difference between toggling and racing, which we will be discussing in the next presentation. So, that is all for this presentation. See you in the next presentation.